We're going to finish up 7-2 today. Reminder that all 3 of your 7-2 Math XLs are due tomorrow night. So hopefully you're keeping up with those 3 little mini assignments. Today's going to be really similar to yesterday. Yesterday we did p-values to do hypothesis testing. Today is going to be rejection regions to do hypothesis testing. This is the more common method because you can visualize where you reject and where you don't reject, versus with the p-values, you have to remember if p is less than alpha or p is greater than alpha, what that means for rejecting and not rejecting. So this one's a better visual, so we use this one more. All right, so a rejection region is a sampling distribution. It's a range of values where the null hypothesis is not probable. So when you reject, it will either be in the left tail, the right tail, or both tails. We've talked about how to find that before. And if you have a z value in the shaded region, that's where the null hypothesis is not probable, which means we reject. So if we're in the rejection region, we reject, which is where it gets its name from. If it's not in the rejection region, we don't reject. So the steps that we're going to use here are, again, really similar to yesterday. The only one that's slightly different is instead of having a p-value and then comparing it to alpha, we're going to find the rejection region using alpha. So it's this third step here. We know how to find if it's left tail, right tail, or two tail. If it's left tail, we're going to take our alpha, which is often 0.01 or 0.05 or 0.1. Remember, those were the most common ones. And we're going to find that area in our z-score charts. Remember, we've done that before, where you find the area in the middle of the chart, and then you look to the left and up to find the z-score that goes along with it. The z-score that goes with that area is where the shaded region starts or stops on your ends, on your tail. So that's how we do it for the left and the right. If it's two tail, we take our alpha and divide it by 2, because the shaded region covers that area total. And then we use half of alpha to find where that critical value is. So that's the first thing we're going to do here. Now, what I want you guys to do on your purple packets, these values are not listed on your z-score table, but when you get your charts, when we do test day, these values are on there for you. Okay, so I want everything to be in one place because we use these so often. So take these values on your paper, and I want you to put them on the z-score chart. I don't care which side of it, either the positive side or the negative side, but put it on your z-score chart on one side where you've got some space. Okay, so these are the most common values of z that we use for those rejection regions based on what our alpha is and what kind of tail test we're looking at. So get these on there first. And then on the right side of the slide in a second, we'll talk about what to do if our value is not on there, if we have a different alpha that we're looking at for the problem. Write that down on our purple packet.
The alpha tail z thing?
Oh, the whole thing on the left there. Alpha tail z. Yep, that's right. It's going to save you time, though, so you don't have to look these up every time. All right, so let's say You have an alpha of 0.1 and it's a right tail test, the z-value of 1.28 is where that rejection region is going to start on the right. Or if you have an alpha of 0.05 and it's a two-tail test, then you're going to have rejection regions that start and stop at positive and negative 1.96. Let's say that we have an alpha of 0.03. So that's not one of the common ones that we use, but possible. And it's a left tail test, which we know we can get from our alternative hypothesis. What that means is in the left tail, we're going to have a shaded region, a rejection region that has an area of 0.03. And our job is really to figure out where that region starts, stops, however you want to look at it. So where that happens is the critical value of z that we're looking for. And sometimes our book uses a z sub 0. I like the z sub c, either one. It's our critical value that we need from our chart. So what we do is, if I know the area's got to be 0.03 to the left, remember that's what our chart gives us, area to the left. So we're just going to look in the middle of the chart for that 0.03 and get as close as we can to it, okay? So the closest I can get in the middle to 0.03 is 0.0301, and that's a z-value of negative 1.88, okay? And then we'll use that in our hypothesis test. Does that make sense? Then let's pretend this problem said instead of left-tailed, just so you have one of each here, it was a right-tail test. Okay, so that would mean the area to the right is a 0.03. Okay, well that's not what our chart gives us. Our chart gives us area to the left. So if the area to the right is 0.03, what's the area to the left? 0.97. So that's what you're going to look up on your chart to find the critical value of z. So, and you're going to notice something here. When we look up 0.97, closest I can get is 0.9699, which is positive 1.88. So whether it's in the left or the right tail, you're actually going to get the same absolute value for that z-score. Okay. If it's a two-tail test, that area of 0.08 is the area total in both tails. So that means we're going to divide it in half. 0.04 is on the left and 0.04 is on the right. So I'm just going to look up the one on the left, and I know I'm going to get opposites here, one positive, one negative. So if I look up 0.04, I can get, how close can I get? 0.0401, and that is at negative 1.75, so plus and minus 1.75 would be the critical values of z that we would use for those rejection regions. Okay?
What equals 0.0?
A, that's an A, they're all A's. Sorry, that one got a little smudged. There we go. Okay, makes sense? So most of the time, they're going to be the ones that you guys have written on your chart. And again, these will be written on your chart when you get your chart for the test. But if it's not, that's how you would find it. All right, next slide. Not that one. Nope. Maybe. Yeah, okay. All right, so this slide's kind of what we talked about already. The left tail, right tail, and two tail tests create a rejection region, a shaded region in the left tail, the right tail, or both tails. We're going to use our critical value of z, and again, you can see that our book uses a z sub 0 instead of a z sub c, same thing. And we're going to calculate our own z value from the statistics and the hypothesis test. If our z value is in the shaded region, we reject. If it's not in the shaded region, we don't reject. So that's how we can kind of visualize making that decision versus like the less than greater than thing we were having to do with the p's. So on this slide, all we're doing is using the rejection regions that are set up at the bottom. So this was a two-tail test, you can see. And based on the z values we're getting at the top from some hypothesis test, making a decision. Are we going to, from that z value, either reject or not reject? So it's just like multiple choice question, right? So 1.98. Is 1.98 in one of my shaded regions in the bottom? Yes, 1.98's over here somewhere. So because it's there, I would reject. And remember, we are always rejecting what? What's being rejected? The null hypothesis is always what's rejected or not rejected. Okay, what about negative 1.89? Would I reject or not reject based on that z value? negative 1.89 in one of my shaded regions. No, it's in the yellow over here somewhere. So we would not reject, or you could say fail to reject the null hypothesis. Okay, what about 1.65? No, it's over there somewhere. Fail to reject. Okay, and what about negative 1.99? That guy's on the far side there, so we would reject the null. Okay? Questions there? Making our decisions. All right, let's do a hypothesis test. Most of these steps are going to be similar to yesterday. Instead of at the end getting a p-value and an alpha and comparing them, we're just going to get the rejection region and compare our z to it and make our decision based on that. A researcher claims that the mean annual cost of raising a child age 2 and under by married couples in the U.S. is no. Is that the first problem you have on your slide? I feel like it's not. What happened to my other slide? Where did it go? Shoot. Hold on. Is it the problem about employees? Okay, let me just capture that. I don't know how that got deleted. I got it. Okay, better. All right, so employees at a construction and mining company claim that the mean salary of the company's mechanical engineers is less than that of its competitors, which is $88,200. A random sample of 20 in the company's mechanical engineers had a mean salary of $85,900. Assume the population standard deviation is 9,500 and the population is normally distributed at a level of significance of 0.05. Test the company's claim. All right, so same things we're going to check at the start that we were checking yesterday. Number one, do I know the population standard deviation? What is it? 9,500. Number two, is either my population normally distributed or my sample size bigger than 30? Normally distributed right there, okay? And if it wasn't normally distributed and we didn't have that sample size, because our sample size here is only 20, we would just say the hypothesis test cannot be completed, and we would just stop. That would be it, okay? All right, what else do I know? I know my sample size. From that sample, we have a sample mean of 85,900. We have a level of significance of 0.05. And then we have the claim, which is going to include that population mean value that we're going to be testing. Okay, the claim here is that the mean salary of companies' mechanical engineers is less than that of its competitors, 88,200. So the mean salary is less than 88,200. Is that going to be a null or alternative? Alternative. And we're always hypothesizing for now about the mean, less than 88,200, and we label it the claim. Okay, so if my claim is the mean is less than something, what's the other one is going to be greater than or equal to? Remember, equal to is always going to be in your null, not equal to in your hypothesis. Also from that, I can say whether this is a left tail, right tail, or two-tail test. That comes from my alternative hypothesis. This is a left tail test. Okay, we are ready to get our rejection regions. As soon as you know what your tail is and you know your level of significance, you can find the critical value of z. 0.05 is one of the common values, so it's one of the ones you guys wrote down on your chart. We find 0.05, we find left tail, find where those intersect. And we're going to get, and I'll use the 0 here because that's what the book uses, negative 1.645. Okay, so that is where our shaded region on the left, I guess, stops. Okay, so anything smaller than that, what we get for our z value would reject. Anything bigger than that we get for our z value, we would not reject. So let's calculate our z value, just like we did yesterday, and see where it falls. So the formula yesterday was x bar minus mu, so remember it's always sample minus population on the top, divided by standard deviation over the square root of n. And we have all these things already. So 85,900 minus Remember that mu is always coming from our claim and our hypotheses there, over 9,500 over the square root of 20. So I get negative 2,300. I get that's all right. Yeah, 2124. I missed a decimal on mine, 0.26. There we go. Negative 1.08. Is that right? Okay. All right. So now we just want to see, is negative 1.08 in our shaded region? Yes or no? It is not. It's over here somewhere. So if it's not in the rejection region, what's our decision? We fail to reject what? The null hypothesis. Okay, so then we summarize, same as yesterday. So we say there either is or is not enough evidence. So if we don't reject, there is not enough evidence to, and then we either say support or reject the claim. And when you get to the test, it's going to ask you to put the summary in context of the problem. So we are supporting or rejecting the claim about mechanical engineering salaries. Okay, so just going back to what this is ultimately representing. So are we supporting or rejecting here? Why do we use the word support? Right, because the claim is the alternative. And here's why. If we don't reject the null, we don't have enough evidence to say that this isn't true, which means we don't have enough evidence to say that this, its complement, is true. We can't support this because we can't throw this guy out. Does that make sense? Okay. What questions do you have on this problem? None? Okay. No. There's 2 more problems on your paper, but I'm only going to make you do 1 more. How about that? That'll be my deal. All right. You guys try this one. I'm going to have you put answers up on the board.